To make some of the issues we're going to be talking about simpler, we're going to focus in on, in some sense, very simple kinds of problems that take input, just like we've been looking at, be it a graph or a list, whatever it happens to be, and processes that to get an answer, and the answer is just 0 or 1, yes or no. So that's the sense in which it's making a decision. It's making a yes-no decision based on the inputs. An example is graphed connectivity, where you're given a graph and you're asked, are all the nodes reachable from all the other nodes in the graph? And the answer is either yes or no. It's either connected or it's not connected. So even though this output is very, very simple, just 0 or 1 bit, it can actually be fairly complicated, sometimes very, very complicated, to take the input and decide whether it's a 0 or a 1. Here's another example. If I give you a graph and a node V and a node U and a number K, those are the inputs, the question is, can V be reached in fewer than K steps from U? Another question is, given a graph, is it a tree, yes or no? For it to be a tree, it needs to be connected and not have any cycles in it, no loops. Another decision problem is, given a graph, is there a bridge link somewhere in the graph, an edge that if it gets removed, separates the graph into two separate pieces? Given a graph and a number K, is there a pair of nodes that are K steps apart, that the shortest path between them is no more than K steps? Another question is G bipartite. This was a homework problem, or there was a closely related homework problem, where you can take a graph and try to work out whether it is separatable into two sets of nodes with edges only going between the sets. Now, you could argue that in some sense these problems are all a little bit silly. We don't often want to know just one bit of answer. We want to know something like, not, is there a pair of nodes K steps apart, but find me a pair of nodes K steps apart. Or is the graph bipartite, but separate it into the two pieces and show me what those pieces are. Or can V be reached in fewer than K steps from U? Well, if it can be, show me the path. I would really like to know the path because that's what I'm going to be able to work with. So an interesting fact about decision problems is they're often directly relatable to the version of the problem that you're interested in that actually gives the answer. And sometimes you can actually connect them with only a polynomial amount of extra work. So basically, if the decision problem is efficient, so is the problem that returns the more interesting input.